Hi everyone. Today I will be talking about the construction of a family of Maxfaces, and we'll see its singularity analysis, moreover the swallowtail and cone-like singularities. So before going on, let's see some definitions. So what is max face? So let X be a smooth map on a two-dimensional oriented manifold M. Then if the pair this XM, if it satisfies the following condition, that is the pullback metric on that the pullback metric is positive definite for almost all P in M, and the mean curvature is zero almost everywhere, and the map is immersion for almost everywhere. Almost everywhere means except the zero major set. Then we call this pair as generalized maximal immersion. And the set where the map fails to be immersion, we call them singular points of the map. And a generalized maximal immersion is called max face if the differential map has exactly rank 1 at all the singular points. So they are similar to the minimal surfaces, which are zero mean curvature surfaces in R3. But here, because of the metric, non-isolated singularities generate, and which and there are other things like, for example, there are lots of complete minimal surfaces, but the only complete maximal surface is a plane. So similar to minimal surfaces, we have Weierstrass-Enneper representation for generalized maximal immersion. This is a method to construct a generalized maximal immersion. So for this, we needed let M be a Riemann surface and G and DH be a pair of meromorphic function and holomorphic one form on M. So if the map X from M to E1, that is the Lorentz-Minkowski space, if it is defined as real integral of these three components, then these maps give a generalized maximal immersion if the pair G and DH satisfies the following three conditions. The first condition says that the each component of this integral is holomorphic. And the second condition says about the regularity of the map X. And the third condition says that the real integral of this each component is zero, which we require for the map to be well defined. And so it is independent of the path integral. And we call this triplet as the Weierstrass data for the X. And we see the induced metric through this map X is this. And we see the points where the metric degenerate, we call them singular points. So the point singular set for this map are the points where either mod G of P is 1 or where the it is 0 of the holomorphic one form. So let us see some singularities, cone-like and swallowtail singularity. So let X be a max face and sigma naught be the set of all set of singular points. So then a point P belongs to sigma naught. It is called generalized cone-like singular point. If sigma naught is connected, it is compact and its image is single point. Moreover, if there is a neighborhood U of sigma naught such that the image of U minus sigma naught is embedded, then we call this point as cone-like singular point. So Umehara and Yamada, they give conditions to check the nature of a point, singularity, in terms of the Weierstrass data. So these are the conditions. And similarly, we have for swallowtails, these are the conditions to check that the point is a swallowtail or not. So in the literature, we have seen that while constructing the maximal maps, so various question arises, like if they are embedded or not, they are complete or not, what type of ends they have, and what genus we can create, and what is the nature of their singularity. For example, the Lorentzian catonoid, which is a genus 0 maximal map, and moreover, it is complete embedded, and it is a max face with two catonoid ends. Then Kim and Yang give a family of complete generalized maximal immersions, maximal surfaces, and we see that these surfaces are not embedded and even they are not max faces. And this family is of higher genus, like this family MG, where G is the genus. And it has increasing number of swallowtails. As the genus is increasing, the number of swallowtails are increasing. Similarly, we have other theory. So in this work, which was joint work with my advisor and all, so in this work, we want to construct a one parameter family of max faces, which are complete, embedded, and which are of finite genus, and where we can also take finite number of ends, and the ends will be either catonoid or the planar ends. And so this family looks like the horizontal space-like plane connected by some small necks. So to construct that family, we need some input data. So for that, so let us consider L horizontal planes, and just for the convenience, let us label them by small integer L, and let NL be the necks at each level. That is the number of necks which are connecting the two consecutive planes, and let capital N be the total number of necks, and let associate we associate PLK, the complex number, to just give the position of each neck, and then we associate to each plane we associate a real number QL, which will tell about the type of end, which end will be this. So let P and Q be the sequence of these PLK and QL, and we call this pair as configuration. So now given a configuration, let CL be the real number, which give the size of the necks in each level. Okay, and for each neck LK in a configuration, for we define force FLK corresponding to this, which is defined like this for each point PLK, and so here it is not like the force is something needed, since this term is turns out while solving the conditions. Okay, and we call this and it is similar to electrostatic force, so that's why we call it force. And a configuration is called balanced if it is 0 for all L and for all K, and we call it is rigid if the differential of F with respect to P has a complex rank. Similarly, we defined W as this, which is 0, which is necessary for it to be balanced. So this is the main theorem. It says that if we have a balanced and rigid configuration such that the differential of W has rank 1, then for sufficiently small t, as I said, we constructed one parameter family. So this T is that parameter which is greater than 0 and real parameter. So for sufficiently small t, there is a smooth family of complete Maxfaces whose genus is this, where n is the total number of necks. And these Maxfaces have this following asymptotic behavior as t is tending to 0. And moreover, this each MT is embedded in a wider sense. Wider sense means the map is not completely embedded. It is embedded outside a compact set, the set which containing the singularities, if the QL satisfy this condition. So let us see an example. So this is an example when we have, this is the image in E13 when L is 3 and first two planes are connected by one neck, and M is 5, the second and third plane. So if we see that it looks like that they are converging, the singularity image of the singularity is 1 point, but this is not the case. If we zoom out, it turns out they are cuspidal and swallowtail singularity. So to construct this family, we use the Weierstrass-Enneper representation. For that, first we need a Riemann surface. So how we construct? So to each horizontal L space-like planes, we associate a copy of complex plane, which we can see as Riemann sphere minus infinity. So let us go to the picture. So let us suppose that these are the complex plane copies, and to each complex plane, we associate a point ALK, and corresponding to the ALK, we associate a point BLK in the next copy of complex plane. And then since we have finite number of an x, so we can choose an epsilon, and so that we can choose a neighborhood around each point, which is disjoint. So for t greater than 0 and less than epsilon, we remove the disk from the neighborhood of each points. We remove this disk where BLK are the chart around ALK and WLK is the chart around BLK. And so we get these type of annular regions, and then we identify these annular regions, okay, such that the inner radius is going to outer radius of the other annular region. So this is the picture kind of when we compactify it. Okay, and this is the canonical homology basis. So it contains only the curves in the necks and the curves which are going from one copy of complex plane to other copy. So then we define the Gauss map and the height differential, and we solve the period problem. So in this way, we see that we get a family of Maxface. So here, see this family is coming from this. So T. So whatever if you change the size of the disk you removed, you will get a new Riemann surface. Okay. And so the singularity set of this Maxface turn out to be the points where mod GZ is 1. And it turns out that the singularities are only in the necks. And then we examine the behavior of the singularity, how it is changing with the change of Maxface. So what it says that let us suppose if theta is a cuspidal edge for some Maxface, say xt naught, and we have some conditions, then we see that around t equal to 0, there is a neighborhood w theta, such that for every t in this w theta, and t is non-zero, the cuspidal edge remains to be cuspidal edge for every Maxface for the t non-zero in w theta. Similarly, we prove for swallowtail that if theta is swallowtail, then again there exists a v theta neighborhood of t equal to 0, and for each t non-zero, the singularity of Maxface x theta will remain either a swallowtail or it change at most either to cuspidal edge and cone-like singularity. Okay, these are the references. This is the main paper we use to for the construction of that, but singularity is different. Thank you.
Thanks, Anu, and questions are welcomed.
That the traceset method is for the minimal surface or the maximal?
No, it was for the minimal surfaces. He gave a family of minimal surfaces.
So you
So
can
we-
do all these things in minimal surfaces.
Yeah, with the not all these things means, yeah, the construction is kind of same. Here the metric is changing just.
So what is the difference here?
So, for example, even the Vistras representation will change, the sign will change, and corresponding when you solve the period problem, just those things will different. So, main theory was the singularity analysis. Construction was almost same.
Okay, thank you.